Okay, welcome back, everybody. Let's get started. Before we get into the content, today will be about, I'll be talking about perception, about the human visual system, and of course, I'll be focusing on how this applies to visualization. But before we do that, administratively, we just posted homework 1. And here's a little pro tip. The homeworks will get harder and they will take longer as the semester goes on, right? Because the complexity of the homeworks will be increasing because you learn more about, JavaScript and so on. So you should really do all of the ones at the beginning and not use any late days for the ones at the beginning, right? I'm suspecting that homework 1 will take you probably less than an hour or maybe an hour, right? But homework 5 might take you a couple of hours. So if you want to maximize your points and be efficient about it, then you definitely want to make sure that you really do the homeworks in the beginning, like homework 1, homework 2, homework 3, on time. Don't use any late days for them. Just a tip, of course, if you want a perfect score, you do all of them. But if you want to optimize the workload, you definitely want to make sure that you do the ones that are front loaded. Any other administrative questions before we get started with the lecture? The slides there, I posted the slide. I always post the slides after the lecture. You can also look back at last year's website that has the slides are not going to change a ton, right? So if you want to prepare or to have something to take notes. And I post them on the schedule, but I'll usually also post a link on Slack. Yes? Not today. Occasionally. I can give a warning if you want to, but mostly it's going to be group activities, and you're not going to have your own computer. So if you have one computer to share, when we're looking at interactive visualization, for example, that should be sufficient. Today will be paper-based. Other questions? Okay, well, then let's get started. Let's talk about perception. So there's 2 different words here, actually. There's perception and cognition. And perception really is kind of our low-level identification and interpretation of sensory information. So when my eye sees light, that's perception. When my ear hears sound, that's also perception. So perception is all about from the physical stimulus, like the electromagnetic or the sound wave that stimulates kind of something among our sensory organs, to kind of that signal arriving in the brain. However, our perception is also shaped by learning, memory, expectation, and of course shaped by evolution. And cognition is kind of the high-level process, and in some ways you could even consider perception as part of cognition. But cognition is this processing of information. So that basically what happens when me translating the information that I'm getting, the light that you are all emitting, that I'm seeing, that I kind of can translate this, oh, this is a classroom. I can make the interpretation here. So one simple example is hear somebody speak, that is perception, but actually understanding what they're saying, that is cognition, right? So learning something and understanding the language. And so perception really deals with the eye, the optical nerve, the visual cortex, basic perceptions, also some first processing. Some for example, we have natural edge and plane detectors. It's not usually a conscious process, and it is also reflexive. Cognition, on the other hand, is recognizing objects, like this is a chair, this is a water bottle, relations between objects, like this water bottle rests on this table. I'm kind of making inferences about a physical model here. Conclusion drawing, problem solving, learning, or anything else. And so this is kind of a neat illustration between perception and cognition. You see text here. The text is the names of colors, and these are actually inconsistent with the color they appear, right? So you see the top left one here as says red in text, but perceptually it is green. So I think that there's usually a big difference what is there versus what we do see, because our perceptual and our cognition is really shaped by everything that we've learned about the world. So this is one of these emergence images. Raise your hand if you can recognize something here. Well, maybe 10% yet. Who can't see anything? Okay, so here, there's a dog, a Dalmatian. This is the head. Here we have the leg, the front hinds, and this is the body, and here we have the legs. Can everybody see it now? Okay, so these images are kind of like interesting, right? Because they kind of like we see this emerging pattern, even though we don't actually see all of the contours. And we'll be talking about this later today when we talk about Gestalt principles. I think it's just like a scene on the street. So I would say this is probably here is a tree and some garden around it, right? So I don't know the input image, right? But I'll show you the next image here that has a similar thing, and here you'll see like the whole input image or parts of the input image. So can anybody spot anything here on those on the left, on these like dots? I'm guessing not, because it's hard to do. What this is like a segment of that image, right? So we don't actually, like, I'm not showing you the full object. Now I'm showing you the full object. Anybody can see the full object? Yeah, it's an elephant, right? And so like something is going on in our brain that allows us to take this pattern and match it to an elephant. But interestingly, like now, if you look closely, those images here, like this is the trunk, right? And these are the like front legs, and here's some of the ear. So now that you know it, you can also see it in the dotted image. But you can perfectly see this in a high quality render, right? So like you would be able to recognize the elephant in this high quality render, even though it is the same segment as this one here. Why I'm showing you this is that I want to make the point that our perception is based on priors. We have this model of the world. We have an understanding that doors and windows are rectangular, that the floor in a room is flat, and we apply all of those things. And it's kind of like weird for us if it isn't actually the case. So we try to fit what we see into our predefined model, and we get confused if something we see doesn't fit our priors. And I'll show you a couple of examples where you will be confused and only later understand what is going on. So here's the first one. Like this looks like a 3D scene, right? But you, like just by looking at the texture of it and the context, right, you understand this is actually a drawing. But somebody kind of like played a trick on you by like really like working on the perspective perfectly. So, but you perceive this like as actually a three-dimensional thing, even though it is not, right? But this is just because we have these priors that this should appear three-dimensionally. So similarly, if you have these pictures here, right, we tend to like, this is weird. Like, why is there like a human with a dog head, or why is there like this boy without his own head and his head in the sand, or what's going on with these two ladies here, right? So these are kind of like we make assumptions about the continuation of a body where a head is supposed to be, and if we see an image that doesn't conform to that, it kind of confuses us. And there's also this phenomenon that's called Peridolia, and that is kind of the phenomenon of us interpreting something when there's nothing, right? We tend to see faces. This is the toast of Jesus, right? That you've probably seen before, or hear the sad cucumber, or like the sad airport lounge chairs. And like this is important for visualization because this also applies to patterns, right? Like we might see patterns when there is actually none of them. We have to be aware of that kind of information. So the take-home point of this is that vision is constructed top down from the input. So what you see when you see a thing depends on what the thing is, but what you see the thing as depends on what you know about what you're seeing. So now taking a step back and going to the perceptual level and talking a little bit about the eye, you might have heard some of this in high school biology, but I'm sure it's been a couple of years for most of you. And so let's do a quick review and also like I'll make some points about how this is relevant for visualization. So you've all seen these diagrams of the eye, the human visual system. I'm not going to go into the detail about like the lens or the pupils or anything like that. But what I want to focus on is like the rods and cones in your eyes that kind of like make perception really happen. And so we have two types of sensors. These are the cones and the rods. And all of you probably remember that cones stand for color vision, and it's easy to remember because both of them start with a CO. And the cones, they're kind of like super dense around the fovea of the eye, right? This kind of like particular point here in the eye where we have this extremely dense cluster of these cones. The cones do require more light than the rods. And so this is the reason why we don't see color at night, right? We see essentially at night, the cones aren't really functional because they need more light for stimulus, and that's why the rods kick in and the rods do black and white perception. And the interesting thing about the fovea is it has 27 times the density of the rest of the eye. So this is responsible for our sharp central vision, and we tend to only have cone cells in there. And this diagram here shows you kind of like, from the fovea, like if you go outwards on both sides of the eye, of course, in a sphere, how dense is the proportion of cells, of receptors on there. And you can see that like around the fovea, we have this extremely dense concentration, and then it kind of tapers off very quickly. And then we have kind of the blind spot where the optical nerve exits the eyeball. And then, like, this is like these experiments that you can do by moving something around that blind spot that you would miss. And so you have many, many more rods than cones. There's about 120 million rods that are really black and white vision and that are much more light sensitive. And so here's like a diagram of these cones and rods, the rods being sensitive to black and white, the cones again for color vision, and they're then connected to the ganglion cells. And here's some like electron microscopy images of those. And so you can see that the cones are much smaller. And here's like an image for the color sensitivity. And what you also see here is that we have a lot more red receptive cells than green receptive cells than blue receptive cells. So there's only about 2 to 6% of our cones actually perceive blue. And actually, there's very few of them in the fovea. And that's kind of like weird. And people don't actually know why and what's going on, why we still can see blue roughly. Well, not quite as good as the other colors, but we can still see blue better. And kind of like, we still don't know why. There must be some boosting mechanism. That's why we can also see blue relatively well. And so here's kind of like this diagram from earlier, split up into cones and rods. Like you see that essentially the cones are really very central around the fovea, and the rods are everywhere else, right? And the other thing that is interesting is these, like we have these 3 different types of cones. The blue, the ones that are mostly receptive to blue, mostly receptive to green, mostly receptive to red. And what we see here is this isn't like binary, right? This is not like the blue cones will see only just blue light of one wavelength, but this is like a curve. So basically the light of a slightly different wavelength will stimulate it a little bit less. And if it kind of gets into this green territory, the blue one will be stimulated even less, and so on. And so we construct, like we have these 3 receptors, but actually we perceive millions of colors, right? We can tell them apart many, many shades. And the reason why this works is because we kind of like interpolate, like our brain does this processing. And we work in some sense like pretty much like a display, right? Or like a camera. They have the 3 different sensors, and then we mentally blend these images, the intensities together to perceive all of these different colors. So there's one very big thing which we're different from your typical camera. If you were to look at a spreadsheet, and if you were to absolutely not move your eyes, right? This is actually what you would see. Like we tend to perceive everything as sharp because we're good at jumping around with our gaze. But in fact, what we see is really only one thing in the very center, like as a sharp image. And so you can like make this experiment, like essentially, for example, if you like focus on this green bottle here and look there, you will actually not be able to perceive me sharply, right? But you can see the bottle, but by simply moving your gaze around, everything looks like it's sharp to you. This is very different from a photograph. A photograph, if it's in focus, will have everything represented as sharp. And so the human visual system works as the sequence of fixations and saccades. So we have these fixations that maintain the gaze on a single location for somewhere between 200 and 600 milliseconds, and then the saccades move between those different places. These usually take between 20 and 100 milliseconds. And so in that sense, the vision is not similar to a camera. As I already mentioned, what will happen here is that, for example, if we look at this person here first, that we will actually not see this guy here. But if you look at this person here, we will see her as blurred, right? And of course, we still perceive things out here, especially motion, right? This is kind of like an evolutionary trait that we developed so that we see an attacker approaching, but we don't see things sharply in our peripheral vision. So vision is really this dynamic and ongoing construction project. And so this is like what a video here that shows you aggregated eye tracking data. If you showed this video to 50 people and then kind of create this heat map for hotspots and where they're looking, this is roughly what you would see. This is like an ad. So this is like, for example, technology that would be used in analyzing marketing material, or like in this case, diapers. But the point here is that you can see what people are focusing on, right? And so we tend to focus, if we have a scene with humans in them, we tend to focus on humans. Like, for example, nobody here was looking at the door, but everybody was looking at the human in the scene, right? So, and that's why you also might not have remembered the color of the chair, because you were focusing on this one particular face that is very central here. And these eye tracking experiments are actually fun to run, and there's plenty of visualization research that you can do with these eye trackers. And so here's kind of like an example of a fairly, let's say, high precision, maybe old school setup, where you put somebody's head on a chin rest, and then you have a monitor with a stimulus, and then you have infrared cameras that shine light into your eyes, and then you have like a camera that records exactly your pupil position, and then by doing some smart registration, we can tell exactly where people are looking. And these devices are now fairly cheap. You can like, I looked today, you can actually buy them for gaming, right? It's $200, you can connect them to a computer, and so you can kind of like steer a camera in a game for it. They're still like a little bit more expensive for research, because usually you want higher precision, and you also want analysis software with it. But it's the same basic setup. And you can also do this with do-it-yourself kits, which is like basic webcams, and then like buying some infrared LEDs and like building your own rig. So if you're a do-it-yourself person, you can set this up. And so here's another example. This is like a video of somebody singing karaoke. Okay. And this is a demo for this tool. So they're like showing you different representations here. But the point is, you also saw how we read here, right? We actually don't read by continuously moving our eyes, but by moving these fixations and having the saccades in between them. So we read like one or two words, then move our eyes, one or two words, move our eyes. So going back to this like general purpose vision versus our priors, is like the point here is we don't have a general purpose vision system. So what we see really depends on our goals and expectations. So relative judgments tend to be strong, and absolute judgments tend to be weak. One example of how our priors deceive us is this Ames room. And so you see this room where you, like, it appears that you have three people standing here, one being like very small, one being very tall, and the other one being like about average height, right? But this is actually a trick. And what's going on is this room is actually not the way we perceive it or what we expect, right? It is a room specially constructed for that illusion, where you have like a deeper end and a shallower end, or like a closer end, and you place those people accordingly, and then you perceive them differently. And so here's a video that shows you exactly the same thing of a person moving through such an Ames room. So, and this person will appear to be like shrinking and growing as they move around in the space. And then when you move the camera, you suddenly have an understanding of what's going on. Okay. So next topic, color. And color is this incredibly complex thing that, like many of the things that I'll be saying, are actually not completely the final truth. But you know, color is complicated. There could be like its own lecture, like probably like a whole degree just on color in terms of complexity. The physics are insanely complicated. I'll do like a pragmatic approach, and there's like lots of also color models that are also fairly difficult. I'll give you some advice here, but we'll try to kind of like keep it within a reasonable time frame. So the basics of color is the visible part of the electromagnetic spectrum, so electromagnetic waves or particles with like around 390 to 75 nanometers wavelength, right? And the spectral colors are the colors that are evoked by a single wavelength. And these are often called monochromatic colors or the rainbow colors, because this is exactly what they are. Like the rainbow is made up of these spectral colors. And so these would be colors such as red, orange, yellow, green, blue, and violet. And all other colors are unsaturated colors, and they're a mix of multiple wavelengths. So for example, purple, magenta, or gray, like the achromatic colors, anything that is white or black or gray, will be like a mix of multiple wavelengths. And color is, interestingly, is not the same as wavelength, right? But rather it's a combination of wavelength and energy. So for example, if something, like we have these two different curves and we have like a high energy density that peaks around the yellow wavelength spectrum, we will perceive it as yellow. But if this peak is less strong, if we have less intensity here, and there's more of a mix of other colors, we will perceive the same thing as brown. And interestingly, color vision is actually fairly irrelevant to much of your normal vision. So if you like had absolutely no color vision, you would be perfectly capable to survive, right? There's certain tricks that you have to know, is the kind of the order of the traffic light lamps and things like that. But generally, color vision isn't super relevant to our basic survival. It doesn't help us perceive the layout of objects. It doesn't change how we're moving. It doesn't tell us what shape they are. But one thing that color does is it breaks camouflage, right? So for example, if we have like a deer in front of like a forest, we might see the deer because it pops out in terms of being brown instead of green. And one theory that why color developed is maybe also breaking camouflage, but maybe also judging the quality of the food. So for example, we can distinguish a rotten apple from a good one by its color. So it tells us something about material properties. And color has these dimensions. So color, if we talk about it in terms of visualization, we have hue, saturation, and value. And hue is kind of like the thing that, like, you know, we tend to say color, but sometimes mean hue, right? So red is a hue. And then we could say, is it light red? And then we kind of like also talk about saturation. And so saturation would be the purity of a color. And so if you think about, and there's two very different ways of thinking about how color is created. Color is created either by pigments, and that kind of like then light reflects off that object that has these pigments of that certain wavelength. Or color is like, when we think of light, then it's actually just the wavelength, right? So like basically this is important for printing versus displays or projectors, right? And so we have used these two different approaches, pigments or light sources. And so when we think about saturation, when we think of pigments, then no white or black is added. So these are like purely colored pigments. When we think of light, it's about this ratio of the dominant wavelength versus everything else, right? So like what I showed you earlier is this very strong peak that would be like a high saturation. And then value or luminance or brightness is the lightness or the darkness of a color. In general, this is the overall intensity of light. And so you can kind of like in the HSV model, the hue, saturation, value model, you have this color cone. And on the outside of this cone, you rotate through the hue. Then as you go towards the center, you change saturation. And as you go towards the bottom, you change value, right? And these are color models. And there's, of course, other color models like it. And so as I mentioned before, pigment or kind of like any physical thing and has like reflects light in some way, right? And the reason why we perceive an orange as color orange is because the material in the orange takes, for example, light of all different spectra, but only reflects the orange part of it, right? That's why we perceive it as orange. The green apple only reflects the green wavelength, and the strawberries only reflect the red wavelength. And so that's the idea behind, or that's what's going on behind these things. And if you're interested in color and color perception, and if you like podcasts, I do recommend these 2 Radiolab episodes that I'm linking here. The first one here is like a little bit older, from 2012. It talks about, like, you know, color perception in humans, and like how did the physics of color develop. And then the second one here is kind of like an update. It also talks about this mantis shrimp, that we have 3 different types of cones. The shrimp has 12 different types of cones. And so they're speculating of whether they can see color better or not. So they're entertaining and definitely recommended listens. So here's a little pop quiz. What are the 3 primary colors? Red, green, blue, red, yellow, blue, orange, green, violet, cyan, magenta, yellow. Who thinks it's 1? Okay. Who thinks it's 2? About half. Who thinks it's 3? Nobody. And 4? Are you guys print designers, the ones that are having their hands raised right now? So the answer is, of course, it's a trick question. The primary colors are a concept that we kind of like depend on the medium. It's all of the above, right? Let me show you, and then we can kind of like review it again. But basically, well, you basically just need to span a triangle, right, in a color space. And so you can pick any colors as a primary color for your medium. That's the idea. And so typically in paint mixing, and what we historically think about primary colors is red, blue, and yellow. And these are kind of like, you know, if you talk about early history of color theory, these were the colors that are considered the primary colors. And so if you're an artist and you mix your paints on your canvas, you would maybe do like, you know, a mix of red and blue to get this like violet color, or mix of red and orange and yellow to get this orange color. This is subtractive color mixing. And the secondary mixed colors you get are green, orange, and purple. These kind of like have been like substituted to some degree by ink mixing. So subtractive mixing of transparent inks. And these colors are cyan, magenta, and yellow. And these are all, they look blue, yellow, and red to kind of some, like, you know, if you think about this slightly naively. But the reason why those are chosen over the red, yellow, and blue ones are because we can kind of like, if you use those colors, we can create more like a wider spectrum. And the secondary colors here are red, green, and blue. And typically in printing, we have another component, like a true black would be like an added pigment here. And so these are also subtractive, like a subtractive primary colors. And then the ones that we as computer scientists are most familiar with is light mixing. This is basically everything that happens on a computer screen or on a projector. So this is like an additive mix of colored lights. And so the difference like between additive and subtractive is, notice that as I'm mixing subtractive, the colors get darker, right? And notice that as I'm mixing in an additive way, the colors get lighter. And so white is actually the combination of all of the different things. And that is the lightest, of course, whereas black is the absence of light in the light model. And the other way around for ink mixing. Okay. And this is kind of like if you use these primary colors, you span a gamut. And so your computer screen has some specified gamut, or gamut, let's call it gamut. And the gamut is the set of all colors that can be produced by a device. And that is driven by this triangle of, you know, here is like the blue, the red, and the green color. And depending on which screen you have, these could be different, right? Like your screen could have like one dot here, one dot here, one dot here. And so that's why, for example, faithful color reproduction on the web is really difficult, because barely anybody has calibrated color screens, right? We have like print is much easier because you have to, the person that's doing the design is often the printer, and there's like ways to check for this. But on our computer screens, they're not calibrated. An orange might look completely different. And usually on a projector, it looks completely different than on like a high quality laptop screen, right? So this is like what's going on here and why these things are different. So the area between these primary colors is what we can show by mixing them. And of course, as I mentioned already, the exact location of the primaries is arbitrary. And then in some fancy color printing productions, and for printing, this is the same thing, right? I use 3 different inks that defines which colors I can create. But I could also have 5 inks, right? Or I could have 8 inks. And then I can kind of like do a non-triangular gamut for my color. Or I could create a display that has 4 different pixels of different colors. That would also be possible, though it's like I don't think I've ever seen one. This diagram that I've kind of superimposed this on is this Cie Chromaticity Diagram. The question I always get is, what does X and Y mean here? And the frustrating answer is nothing really. They're derived properties of this model. But just think about like the meaningful part here is the outer curve here. These are the completely saturated colors that are part essentially of the visible light. And inside of it are all of the colors that exist. And of course, this is not a perfectly faithful representation, because I'm trying to show you colors outside of the gamut of this projector. So this is going to be off, right? But this is like a model that you can think about how color on a screen is created. Okay, so now we've done the basics of color. Now we want to think a little bit about what does color mean for data visualization. So to use color in data visualizations, we usually create color maps. And so what we do is we take some input values and map them to some color. So, and if we have values, and we'll talk more about these properties of data in a lecture in the next week, is what are the properties of my data vectors, for example? It's categorical versus ordered, or is it sequential versus diverging, or is it segmented versus continuous? Is it univariate versus bivariate, right? There's all of these different properties of data that we might want to map that we have to kind of take into account when we pick a color map. And so what we want to do is we want to match a color map to these attribute characteristics. And so if you want to pick a color map, we have to think about these characteristics and what we actually want to show, and then we can apply them. So here, for example, if we have a sequential vector that goes from 0 to 8, we might pick a color map like this, right? That gives us for like a increasing saturation in the blue tone. It starts with like some light yellow. If we wanted to have categorical values, we might pick these kind of like different hues, and different hues are usually good for categorical data. So if we compare this to our sequential color, here we have we use much fewer hues. We use only a single hue for the sequential one, but we use many different hues for the categorical one. If we have diverging color maps, for example, that could be useful for temperatures, right? So if you have below and above freezing, so that it's important for us to know whether water can freeze at a certain temperature of the day. We might adjust our driving to that, for example, or we might be aware that it could be slippery. And so it might be reasonable to encode temperature with at the freezing temperature, we could kind of encode this as white, 0 degrees Celsius, and then everything above that as red, everything below that as blue. We could also choose to not use bins here, but use a continuous gradient, right? This might have certain advantages. We could maybe notice some nuances more readily if we have a continuous gradient as opposed to a bin gradient. Or we could kind of construct a set of bivariate maps or anything like that, right? All of these are possibilities. And so you could use this to label things. So for example, I could label counties on a map. I'm showing you here a tool that's called Color Brewer. And I think this is like a recommendation I always make. If you want to pick a good color scale, Color Brewer guides you through those choices. You say, my data is diverging. My data is sequential. It also does other things like colorblindness friendly color scales and so on. But you can then pick these colors, preview them, and then you can use them in any of your visualizations. The problem with color is generally I am extremely careful and reductionist about using color in visualization. I use it for highlights and for sometimes for categorical variables, but color comp has so many issues. And one of them is that we tend to think of, we have these millions of colors on our computers. why can't we label a million different categories with them, right? And the reason why we can't is because we can actually not perceive the difference. So we, like, as I mentioned earlier, we're good at relative judgment. So here I have like a map of the internet in 2002. Somebody tried to visualize the whole internet in the network diagram, and all the subdomains are assigned a color. And originally there were only these 22 subdomains, and so they used 22 colors to visualize this. And so what this meant is that they actually used 5 different shades of green, right? And now you can tell those 5 shades of green apart if they're next to each other, but you can't tell those 5 different shades of green apart when there's like when there's some distance or some distractors in between them, right? So you won't be able to actually tell which is which. And the other problem here is that those green things might not be more related than the green and the red thing, right? So the color, like if you use hues that are too similar, you're like making some like bad compromises here. And so my typical recommendation would be that you limit yourself to 6 colors at most, and definitely don't do more than 10. Like in like maybe in a super controlled environment where you know people have good computer screens, you can maybe use 10, but mostly you should limit yourself to 6 colors. And so you should generally like not use color for quantitative data. There's some caveats about this that I maybe want to talk a little bit about later. But basically, what you should use is value here instead of a hue. And saturation works, but it's typically not as good. You shouldn't use hue. So here we have kind of like these examples here of like here. I think you can see it best with the. Well, let's do this. You can see it probably best with these like black and white ones here. So you have a color field or like a field here that goes from light to dark, right? From low value to high value. And here from high value to low value, and then you have circular shape, and then you have a grid pattern. If you use this rainbow color map here, you get these kind of weird effects, right? You get these kind of like segments, like the yellow one here is narrow, and you see like this transition, and it might actually not be meaningful, this transition. Why are these segments exactly there? Why is the green one wider than the other one? And so on. So that's problematic. And you could use maybe something like this like heat map here that is just as fine a choice as the black and gray one. The green-red one has other problems, and I'll talk about this a little bit more when we talk about color blindness. So here is an example of fluid flow smoke with 2 different color maps. On the left, we have a rainbow color map from blue to red. On the right, we have a bipolar color map from blue to yellow over like a neutral color in the middle. And so if you look at those 2, which do you think is better? Like you raise your hand and like tell me your opinion. Yeah. The rainbow one will give you more information. Any other opinions? Yeah. Yeah. So you're getting at a good point, right? Like what you can spot very easily is the point of the highest intensity, right? Like we're in this case, this is probably like the most opaque or the fastest flow or whatever is being recorded here. And so from a pure visualization theory perspective, at least like most people 10 years ago would teach you that this one here is the only one you should use, because it has like these nice properties about, just that you can see. And one thing you can definitely see better is you can see the nuance of the shape better, right? Like you can see these continuous gradients. You have like this feeling of what is actually like what the shape is. But maybe like the other thing that is kind of odd is that if we look at scientific papers of people who are not visualization experts, they tend to use this one, right? And some, you could say, okay, this is just bad MATLAB defaults, right? But people are actually smart, and what implicitly I think happens often is when people are using rainbow color scales, is that they want to highlight the maximum, right? And they want to create these like easy to like identify bins. And the rainbow color map itself might not be the best choice, but a multi-hue color map might actually not be completely terrible at that, right? And so basically it is a compromise, and like the one clause that you'll hear me say all over in this class is it depends, right? Everything depends on the context. if you want to like people to understand the overall shape of that flow, maybe the one on the right is better. If you really want to highlight the maxima, because this is where you kind of like need to maybe harden your engineering part, then the left one is better. Another question is, and I mentioned this earlier, is to bin or not to bin. And people in our lab did a study on this. And so they asked what is more accurate and what is more precise. If we show you like a binned gradient elevation map here, this shows you a mountain range, or if we show you a continuous one. And so the interesting thing is that they found is that for this elevation map, they found that the continuous was tended to be faster. So people were were faster at spotting, for example, the highest value when they had these continuous scales, but the binned one was often more accurate. And again, so we have trade-offs here, but I kind of see this as like I tend to prefer accuracy over speed in many visualization tasks, because you typically have a little bit of time, right, to think about something, and the time to perceive something is often negligible. And so, yeah, it's again a trade-off. But if you really wanted to optimize for accuracy, you might want to go with a bin scale here. Okay, one important thing is color blindness. Color blindness is one of the many accessibility considerations we have to take into account when we design websites or visualizations. And color blindness is fairly widespread. I have a collaborator who I'm working with, and he's colorblind, and he uses one of our visualization tools, and we actually use color to encode, and he's sometimes confused, right? So we have to really make sure that our color maps are very accurate. And so anybody in here, like you don't have to share, but if you don't mind, like anybody here colorblind or color weak? A few people. Okay, so there's like about 10% of all males have a color weakness, and much fewer females, and this is probably due to some X chromosomal recessive inheritance. The most common thing is red-green weakness or blindness. And the reason here is a lack of medium or long wavelength receptors, or some altered spectral sensitivity. So we have some green shift in there. And if I were to look at the rainbow flag and have normal color vision, this is what it would appear to me. If I had no green receptors, this is what it would appear to me. And if I had no red receptors, this was what it would appear to me, right? And so, like, just be aware, this is like another reason why using purely color maps for data encoding is often tricky, because there, like, a sizable amount of the population has some color weaknesses. These are like the kind of tests that you would use to see whether anybody has a color weakness. So can you all read all of those numbers? Okay. So like, it's interesting. Like, I think that not all of them are equally easy, right? Maybe this one here is like, what's the number here? Yeah. So that's a little bit harder to read for me than, let's say, the 26 here. But a 73. Yeah. So of course, like, again, this is on a projector. The light here isn't perfect, so take this with a grain of salt. But if you use this in proper lighting with like a proper printout, and that might be a way for you to detect color blindness. And for example, if you run like a user study or a perceptional experiment, you would usually do a test like this before you include a participant in your study, especially if you use color. And so here's just some other examples of how people without certain color perception capabilities perceive the world. So we have a natural scene here. If you have, if you're protanope, then you see it in this kind of like tinted way, and if you tritanope, you basically see the red one. Then you have this blue-yellow deficiency. And this is problematic because some visualizations are really kind of like, depend on color. This is a visualization that I generally like, from the New York Times, and it shows kind of like the budget in 2012, the budget proposal by the Obama administration, and the color highlights whether something has increased or decreased compared to the previous period. And what it's hard to see here for anybody with a color deficiency is those two bubbles here look the same, right? But in fact here, this was a reduction, this was an increase. And so that's like one of the consequences of like not being particularly smart about visualizations. The problem is, of course, green and red have cultural meaning for us, right? Green is up, red is down in some sense, right? And that's why people tend to use them. But now, like, I think this color blindness has kind of like, it's made its way through like all the people that create visualizations, and like, for example, most people now use red and blue color maps instead of red and green color maps. And we can simulate color deficiencies. There's tools that you can upload as like a photo, but the coolest part is in Chrome, in the development tools, and I'll introduce the development tools when we start talking about web development. You can actually simulate a color deficiency in the developer tools. So you can go to the inspector and then go to rendering, and then rendering at the very bottom, you can emulate vision deficiencies, what I'm highlighting here at the bottom. And if I take this red, blue, and green color brewer page and I switch this on to simulate protanopia, we get this result, right? So I can very quickly check a visualization that I see on my web browser with this tool without having to take a screenshot or upload anything like it. Here's another visualization that the New York Times did not that long ago. And I was surprised that they still make these like kind of red-green mistakes. And I ran it through one of these simulation tools, and this is the result, right? So like, it's not accessible to anybody who has a red-green weakness. So the other thing to note here is this color and brightness is relative. And what I mean by that is the perceived brightness of an object is relative to its background. And so here you have like a background gradient and changes from light to dark. And then on top of it, you have these rectangles. And so this here appears as the darkest rectangle. Then this is a little bit lighter, lighter, lighter. This might be the most lightest, right? Everybody see it the same way? Yeah. And now if I add these two bars here that have uniform color, there's no gradient. And now I move them over. We can see that those rectangles are all actually of the same color. And so the thing here is that the context matters, right? The background matters for us in terms of perceiving like the color here. Here's another example. Which one is darker, the upper or the lower stone here? The upper stone is darker. Who thinks the upper stone is darker? Who thinks the lower stone is darker? Okay. What you perceive, yeah. Like, of course, you know that this is, of course, a trick question because it's a lecture about perception. But so in fact, they're identical. And what's going on here is that we have a prior about where light comes from, right? We understand light comes from the sun or from like ceiling light fixtures. And so if something is on top of something else, and there's also this slanting in here, and it looks darker, we kind of like, our brain tells us, yes, with the physics model that we kind of all have inherited, this is like actually a darker color. So it's not kind of red, like it's not like this isn't realistic, right? It would be realistic if I have floor lighting, but if I have lighting from the top, it is not, and we assume that the lighting comes from the top. So this is called the corn sweet illusion. Who remembers the dress? So is it black and blue or white and gold? I think the official answer was it is black and blue. But you know, it's not an easy question because pigment of the color of the dress itself is one thing, but then the light around it is the other thing. And then here's like an animation that just slices out this particular segment. And then there's like this here we have a yellow kind of like, you know, transparent frame on top of it, and here we have a blue frame on top of it that kind of simulate yellow and blue light. And you can see how it could be perceived in both ways. And so is it like, and there's also some discussion about maybe there's some genetic differences. Some people can only see black and blue, some can only see white and gold, others can switch. Yeah, I think the interesting point here is that, you know, light influences objects, and things might not be as we perceive them in their environment. So which of the X's here is darker? Who thinks the one on the left is darker? Who thinks the one on the right is darker? Okay, majority here. May I draw your attention at the intersection here? again, they're the same color, right? And it's the same trick with foreground and background. And they actually, like, I guess this might be slightly lighter than this one here, but it's not that much lighter. It's kind of like this complicated effect. Here we have two colors, and now in this case, they are actually not the same, right? So we have this darker brown and this lighter brown. And we can see that they're actually, in fact, different colors because they're right next to each other, and relative judgments at close proximity are good. But what happens if I move them? Now we perceive them as the same, right? Like maybe not precisely the same, but roughly the same. Like I could have probably tricked you and asked you if you had reversed the order. And this isn't completely academic, right? Like these heat maps is something that we use in biology a lot. For example, if you want to like visualize a large numerical array, a heat map is a good way to do that. But the problem is that it is relative. Like this is an actual heat map from a bio paper, and the authors here in this article, they looked at these two particular values that I'm highlighting here with a star. They're actually the same, right? But we don't perceive them as the same. And so if we make judgments about any peaks or so, or some kind of like gradients, we have to be aware of this interaction of color. Okay, so I want to move on to our first design critique here. And so we'll be handing, like I'll introduce it first, and then we'll be handing out these papers here. And so the way this is going to work generally is there will be some handout, there's going to be some introduction, and then I'll give you like 5 or 10 minutes to turn around or turn to your neighbor and have a bit of a discussion about the questions that are on this particular one. And so I want you to talk about this chart. This is what like a chart that Bill Gates called out as his favorite visualization, and it shows the causes of untimely death. So what are people dying for before they're supposed to be dying, statistically speaking? And it's broken up in injuries, infectious diseases, non-communicable diseases. And I want you to take a look at this chart. But before that, I just want to quote Bill Gates here. I love this graph because it shows that while the number of people dying from communicable diseases is still far too high, those numbers continue to come down. There remains much to do to cut down the death in that yellow block even more dramatically. We have the solutions, but we need to keep up the support where they're being deployed. Okay, so now what I want you to do is like discuss the questions, like what question does this visualization answer? What are some of the design principles that are used in this visualization? Why do you like or dislike this visualization? And you could also talk about the encodings, right? Like how is the data encoded? What is being used to encode the data, and so on. And any other things that you might want to talk about this visualization. Okay, so it's 2:52 now, and we'll start the discussion, and we'll keep the discussion going until a little bit after 3, and then we'll do like a discussion in the group. Let's just hand some back here. You have one? Yeah, if you want to submit it as an activity, yes. Just put it on the back, and then you can upload it to Canvas. So we'll need to upload. You can. There's like we'll do many of those. You have to upload 5 over the semester. Oh, okay. So if you do one today, you have one done.
I didn't get one because like do I have to get one or write down something? Are you going to collect these?
Well, there's 5 activities that you submit over the semester, and you can submit this as one of them, but there will be plenty of opportunities.
Blue and the yellow vest thingy and that brightness relative field. That's how the monitors actually generate the color brown because it's not in the.
Yeah? Okay, cool.
Yeah.
No. Yeah. Bang and Niels Gelnberg, I think. Yes. They can. I'll talk about this later. Yeah. Yeah. Yeah.
No, by chance.
It says cancer. Yes. I think so. Yeah. It's yes, lung cancer, liver cancer. Okay, so let's talk about this all together. First, administratively, this is one of the activities that you can submit to one of your kind of like on Canvas. We have these bins for these activities, and you just put your name and your UID on this sheet where you have your notes, and then you upload it to one of these boxes, and then this will count as one of your participation activities. Okay. Any questions about that? And there's like we're gonna have 20 of those or 15 of those, right? And so if you don't do it today, you can do it another day. No rush. Yes. No. Please take a photo of it with your phone and then upload it to Canvas, because that's much easier for us to grade than if we actually got a stack of 150 paper sheets. Yeah. You can do PDFs or you can do. No, this is just in class, so it's a participation aspect. Yes. Yeah, this is mostly binary grading, right? If you do it, then you upload it, right? And if your friends have the same thing, that's okay. Yes. Five. So we'll have roughly 15 or so over the semester. Yeah. Anytime before the semester ends. So, but I would recommend that you do it now, right? We grade this in batches. If it comes in, and so on. Yeah. Okay, great. So let's talk about the visualization here. What's the data that's being represented here? Like, anybody, just raise your hand if you want to participate. Yeah. Exactly. So this is one aspect, like how, I would not even say count. I would probably say percentage of how many people died or something adjusted by lifespan. Yep. Assuming from, it doesn't say here, but you can probably guess from how many infectious diseases are in here that this is globally, right? Because infectious diseases probably make up much smaller portion pre-COVID in industrialized nations. Yes.
Also saying how would that change?
Exactly. So that's the second vector here. And we have two data vectors. One of them is kind of like the share of that particular disease. And the other one is how it has changed. Okay, so there might be some other things, like maybe there's of course labels, right? And there's also some additional categorization going on here. So we have a third vector that is what? Well, cancer, not cancer is the fourth one, yes. And then we have the third one. That's kind of injuries versus infectious diseases versus non-communicable diseases, right? If you had a spreadsheet, you would probably have these 5 columns, labels, the proportion, the change, which category they're in these top 3 categories, and whether they're cancer or not. Okay, great. So how is the percentages, how are they encoded? Yeah, area. So they're encoded by area here. So the size of one of those little blocks here corresponds to the size of the value, the numerical value. Something interesting about the layout here? Yeah. So yes, that's a good comment. So the 3D aspect of it here doesn't seem to have a particular value. Anybody want to disagree with this? Yeah. Well, maybe, but usually we say that if you have 3D, the text might be even harder to read because it gets distorted, right? So, but yeah, like anybody else? Yeah. Yeah, so it's kind of emphasizing a few data items here that are at the edge. Yeah. Yeah, I would agree with this idea, right? There is like, what is the purpose of a chart? Is it a government report or is it a newspaper article? Do you have kind of like the attention of your reader guaranteed in a sense, or do you need to like compete with other things for their attention, right? Like what might you be more likely to look at, a chart like this or a bar chart, right? So maybe you might be more likely to look at this if it is a 3D blob, a 3D thing with a drop shadow with a nice one, right? So like you're starting to think, why is it this way? What does it mean? So maybe that's worth something, and we'll talk about this a little bit more in the future. Any comments on this? Yep. Yeah, the shadow is definitely not, in terms of precise reading, it's definitely not helpful. Yeah.
All the three things that are at the bottom, they're already represented on the legend.
Yes.
So there's no point.
Yeah, it's a very good, like this is redundant. Redundant isn't always bad, right? Redundant encoding can sometimes be good, but it's not necessary here, yeah? No, you were first, go ahead.
Area is misleading.
So this is a good point, and that's especially true because these rectangles are not of the same proportion, right? They're all of different proportion. Why do you think they are of different proportion? Well, because you want to fit this into this neat layout, right? This is this nested layout that all of the infectious diseases are in one rectangle, right? That's kind of like, that's called a tree map technique, and we'll talk about this in the future. But the result of this is that we have, like, for example, this tiny sliver here where we don't even have a label, right? But the tiny sliver might be about as big as this one here. Okay, so let's talk about the color map. Anybody have anything to say about the color map here and the legend that we have done here? Yeah. Yeah, so that might be a problem. Yeah. So this is actually my biggest complaint about this color map here, right? Because -1% and -1% and +1% is actually the same thing here, right? Like it's almost not noticeable. So what you could have done here instead is you could have maybe done like bipolar color maps, right? That you can very quickly tell whether something has increased or decreased. But it's like, for example, I wouldn't know that malaria, that if I didn't look at the legend, it wouldn't be intuitive for me to know that malaria has gone down, like the share of malaria death has gone down, right? So that would be really hard to, or this is really hard to understand. You have to very carefully look at this legend to be able to read this. Any other comments about the color? Exactly, so they're not consistent. There was one back there. The malaria and HIV, I don't think they're overlapping. It might be hard to see on your print, but there's a little line, at least on like the actual figure that I see on my computer. Yeah. Yeah, so that's an interesting observation. We would have, like, it's hard to tell from the figure itself, right? We would have to look at the legends. And for the legends, I might agree with you, right? This here looks a little bit darker in the yellow one than it does in the green one, right? Yeah. It's not immediately apparent. Yeah, so the borders are usually a problem in these charts. Yeah. So I'm guessing what happened here is that they didn't have space to label it, right? And that's kind of reasonable if you consider the small ones to be not important. But of course, in an interactive system, you could do this in hover. Yeah. Yeah, and I think that because these colors also have like different saturations to begin with, right? This is really hard to do. Okay, so maybe let's take a more value judgments. Do you like this chart? Anybody have an opinion? Like, love it, great idea? I wonder if it's not so much the chart, but how it's presented. Something like this, I feel like useful in practice, where you can put out for the space more directly as opposed to static images. Yeah, exactly. Like if you want to dig deeper into this, an interactive version would be really cool, and you could see much more. Yeah. What I've noticed is that it's a percentage 2005 to 2010. So that means that you probably change the portion of injuries and diseases. But as far as this visualization, those sections are just put out as one. Yeah. So in practice, if you wanted to do this, you would have to have a second chart, right? You would have to have the same chart for 2000 and then this other chart for 2010 or 2005 and 2010. That's a good observation. So okay, here's like a two different takes on this chart, and like you can. I don't think any one of them is better than the other one. They're just different perspectives. So this chart violates a lot of what we teach as basic visualization principles if you want to optimize for like perceptual accuracy, right? If I wanted to know whether malaria or lower respiratory infections cause more death, this chart wouldn't really help me, right? I could maybe make a guess, but it doesn't really tell me this precisely. So a purist might say this is a terrible chart. They might say this is like, you should redesign this with little bar charts. And here's one purist that did exactly that. This is Stephen Few. He runs this Perceptual Edge blog, and he's like a business consultant, like for business analytics. And he says this is a terrible chart because, like, if I did this bar chart here, it might be way more efficient. So one thing to note here is this chart is maybe better if you print it out and have it in front of you, but I think none of you can actually read any of the labels, right? I can read them if I like bend down and look at them. But so it clearly has like less of an overview effect. So what it shows here is the first columns is years of life lost per 100,000 in 2010. This is actually not a number that is contained in the other chart or not explicitly labeled. Then we have a second column here, percentage change in years of life lost, 2005, 2010. And so the first one here is cancer. What you see here is cancer has the most years of life lost. So cancer is kind of like the biggest disease out there, right? It's not surprising. It kind of like is intuitive. And then there's another metric here, death per 100,000. And so this is also interesting, and it's not contained in the other chart. It's not clear exactly. what is actually going on? Is it death per 100,000, or is it years life lost, right? And I would probably argue that years life lost is most often a better metric than the absolute number of deaths. For example, if you talk about COVID, the total case number of people who died is of course tragic, but it's also useful to think about this in years life lost. If you look at this, like here we have these three different things, and then if we had an interactive system, we could potentially sort it, right? We could sort it. What has changed the most? And we could see that we have down here, this is injuries other than accidents and self-harm. So basically, like a lot of this is here is suicide, right? And you can see that suicide has actually increased. So that's an observation that was kind of like hard to make from the other chart, right? And the categorical, like these three different categories, like communicable, non-communicable, and injuries, they're kind of like here shown only as colors. So they're kind of de-emphasized a little bit, right? And so what do you think about this chart compared to the other one? Which one do you like better? Why? Yeah. Yep. Exactly. That's a very good observation. Yeah. Yeah. It looks very government report like, right? And I think it is like if you wrote a scientific paper, this would be the chart to go for, right? But if you wrote a magazine article and want to highlight the impact of the Gates Foundation on like whatever infectious diseases in Africa, then maybe the other chart would be the one to go with, right? And so there's this trade-off that we sometimes make between making something pop out, making something grab our attention, and being precise. And precision is important, and I tend to design my tools because I tend to design for experts. I tend to design my tools with high precision. Like for example, I could have designed this chart, right? This is like something that like I've done visualizations that look like this. I like these tables. We'll actually have a homework that will look like this. But it's not as there's something to say about the wow factor of the other one, even though like 3D and yes, and like hard to read with the labels and the colors are weird and so on. Okay, so this was our first example for one of these design critiques. We're at time. Usually my lectures don't neatly fall into like one topic, one time slot. So I'll be having like another 60 slides on perception next time. So yeah, I'll see you then on Tuesday.